Okay, so it started recording now. Let's go to our notes. Okay, so we looked at quantitative measure of equilibrium last lesson. So what I'm going to quickly do, as it's a slightly confusing part of the module, I'm just going to ask a couple of you a few questions to make sure that you understood it very well. So Gerald, what equilibrium would you be studying if you were to quantitatively measure the K constant at school? Do you remember the reaction?
I knew it had to do with color spectrometry. Is it the iron thiocyanate reaction?
Yeah, very good. So it's the iron thiocyanate equilibrium. So iron 3 ions, they usually be complex to, for example, chloride. So it'd be iron 3 chloride combining with potassium thiocyanate. Here you see the net ionic equation. Okay, good. So can anyone tell me the basis of colorimetry? Whose law or whose equation is colorimetry based upon? Mithilesh?
No, I remember it was 2 words, but that's it.
Okay, Riasad, do you want to help us out? What was the equation that colorimetry was based upon?
Sorry, yeah. It's the Beer-Lambert equation.
Good. What does the Beer-Lambert equation tell you?
The absorbance is directly proportional to the concentration.
Very good, right? So we can use this for colored solution where the absorbance of their light is directly proportional to their concentration. Very good. So Pranav, what's the components of colorimetry? So what are the different components inside the colorimeter machine?
So there's like the light source, which is like absorbing the color of the solution. And
Pause. The light source absorb the color of solution? Are you sure? What I would say is that you have a light source that is releasing white light. Okay, we use a monochromator to select one wavelength that is complementary to the color of solution. And we measure the intensity prior to it passing through the cuvette and after it passes through the cuvette to determine absorbance. So that would be an exemplar answer for the different components and the purpose of colorimetry. Okay, very good. Now, Athavi, you've got an absorbance. How do you find the concentration from absorbance? What must you plot it against?
I forgot the name. That curve, calibration curve.
Yeah, so an absorbance calibration curve. So that's what we've spoken about. Very good. Now, like I told you all, this will be in your exam at the end of this module. So make sure you've read up on it. All right, we'll move on now in this case. So here we have an acid, right? And how do we know this is an acid, Mithilesh? What are the properties of an acid?
I see it as hydronium ions.
Good. Okay, so it releases. For now, we can say hydrogen ions, but you are right. Hydrogen ions themselves don't exist for a long time in nature. They form a coordinate covalent bond with water molecules. I think we've gone through this where I explained to you all that the hydrogen ion is going to form a coordinate covalent bond where both electrons come from the oxygen. So it's not your typical covalent bond. And the hydrogen had a charge of +1. So this entire complex becomes +1 in charge. So whenever you see hydrogen, just know the true formula for hydrogen is H3O+. Okay, we'll come back to that in module 6. For now, all I want to hear is an acid releases hydrogen ions in aqueous solution. Riasat, are acids sour or bitter?
Acids are sour.
Good. And Pranav, are they electrically conductive or not?
Yes, they are.
Okay, very good. Okay. And extension question, Joe, do you know what they do with litmus paper? Have you ever heard of litmus paper before?
I've heard of it. I know that it's like an indicator of some sort. I don't know what it's for. I forgot what it's for.
When you think of acids and bases, Joe, do you have any colors that come to your mind? So acids, is there a particular color that comes to your mind?
Oh, well, like on the pH scale.
Yeah.
It's like red to one side and blue
Very
to the
good.
other.
It's the exact same with litmus paper. Okay, so litmus paper will turn red. So you'd use blue litmus paper and it would turn red for acids. And for bases, you'd have red litmus paper that would turn blue. Okay, these are a few things that will come up in module 6. That's why I'm mentioning it. This is almost like prerequisite knowledge to understand acids and bases for the next module. Very good. Now here you've got the K constant for this acid. How can we simplify this K constant expression? So Ansh, do you want to give it a go? There are two substances in this equation that will always have the same concentration. Do you have any idea what those two substances could be, Anj?
Is it the hydrogen and the oxygen?
Yeah, very close. Are you calling this the oxygen?
Sure.
This equation here. Yeah. So does anyone know the name of this ion, or particularly the name of this acid? Give you a hint if you.
Acetic acid.
Acetate.
Very good, right? The hint I was going to give you is if you like sushi, they put that in the rice. So vinegar, you're literally looking at the chemical formula of vinegar. So acetic acid or ethanoic acid, as you might call it. Small point here, until you do organic chemistry, I need you to understand that this entire unit is almost like its own polyatomic ion, right? So it always comes as a unit, and it's only the final hydrogen at the end that can be released as an acid. So this is what we call a monoprotic, or has one hydrogen as an acid. Okay, very good. So you can see that one hydrogen being released, and it's an aqueous solution, so you can say this is an acid, full stop. Now, Anj is completely right. If we were to do a rice table very quickly, right, the initial concentration of the acetic acid, let's call it 1 mole per liter. Okay, we can say the initial concentration of hydrogen and this ion, which is known as the acetate ion, not oxygen, acetate, or you can call it the ethanoate ion. So Gerald, at time equals 0, what would be the concentration of H plus and CH3COO minus?
0.
Yeah, right. And we can assume that, let's say, it changes by X. So it increases by X units, right? And that would mean your acid would decrease by X. So you can see that at equilibrium, the concentration of your ethanoate and your hydrogen ions would always be the same. So the only reason I'm mentioning this, everyone, is whenever you're doing K constants for an acid, we say KEQ equals to Ka. So if you ever see the expression Ka, it's just KEQ, but they're specifically identifying it for an acid. Okay? It's also known as the acid dissociation constant. Good. Same thing, right? It's this exact same formula. And I guess the simplification I want you to make is you want to make this expression in terms of hydrogen ions, because we can calculate pH, and from pH you can find hydrogen ions, right? Does anyone know the equation for pH? We're not going to go into too much depth on pH calculation. That's again module 6, but this links very well to the basics that you would have learned in year 11. So let me ask Athava, what is the formula that you might remember for pH?
I'm not really sure. It's like, I think the log of the hydrogen ions, or 1 over hydrogen ions.
I would say it's the negative log of the concentration in moles per liter of hydrogen ions. Very good. So in year 12 chemistry, you will typically be working towards finding pH or finding hydrogen ion concentration. So that is why I want your equation to be in terms of your hydrogen or hydronium ion. So we can simplify our equation to this. Right? That's it. So I just wanted to emphasize that. So for acid calculation questions, I think it's still good to do a rice table to start off with, everyone. But when you get confident enough for acid and base K constant questions, you can jump straight into it and understand that it's just going to be hydronium ion squared as your numerator. Okay, very good. And Pranav, I'll get you to make the jump here. What about for a base? First of all, what is the name of this compound, Pranav?
Ammonia.
Very good. And now you're going to learn that it's basic. And what tells you it's basic from this equation here?
Is it the hydro? Yeah.
Good, right? So it's releasing hydroxide ions in aqueous solution, so it must be a base. That's what you've learned up to year 11, right? So that's what I want you to go with. Very good. So since it's releasing hydroxide ions in aqueous solution, it's a base. Very good. What do we call this ion here? Riasat?
This is ammonium. Wow.
Very good. And it's the only polyatomic ion with a positive 1 charge. Okay, very good. All right, coming back to this, how could we simplify this equation, right? Because again, you want to make everything in terms of hydrogen ions and hydroxide ions for acids and bases. So we'd call this Kb, or your base dissociation constant. And I'm not even going to do the Rice table for you. You can kind of do it in your head. What can we say about ammonium and hydroxide concentrations at all times? What must they be at equilibrium? Mahir? At equilibrium, what can you tell me about ammonium ion and hydroxide ion concentration?
They'll be equal.
Yeah, very good. So you can say that's quite literally just OH minus squared, right? And we can divide that by NH3. Now you might be wondering, why have they got water here? Sometimes what people do is they add water, but they just give it 1 when they sub it in, right? So if you're wondering why water's there, it doesn't need to be. You can just imagine it's not. Okay, good. So that would be your answer to this question, just simplifying these acid and base dissociation constants. So I'm going to give you a question very soon on this. Anyone know the formula for pH? Again, this is extension. I have not taught it to you, and you may never have learnt it, but just for those of you who might have learnt this as extension. I'll give you a hint. It's exactly the same as your pH, but instead of subbing hydrogen, you sub in the other ion, right? So Gerald, what would that make it?
Minus log 10 times concentration of hydronium.
Hydroxide. In this case.
Hydroxide, yeah. Sorry.
Good. Now, does anyone know why there is a P? So you see POH and pH. I want you to understand it. What does P mean? It's an old term that refers to power. So power of hydrogen, power of hydroxide. Okay? And does anyone know why we use pH at all? Why don't we just mention everything in terms of concentration? Any ideas? Why make it so complex and start adding logs in chemistry? What's the point of all of that?
Is it to simplify the numbers because they're like really large and there's a big difference?
Very good. It's not just to simplify the numbers. You're very right. One major reason is to simplify the numbers into whole, like almost integers. But the other major reason is acids and bases can have hugely varying levels of hydrogen ion concentration, where one acid could have, 1,000,000 times the hydrogen ion concentration of another acid. And so it's very difficult for our brains to comprehend what it means when you have 1,000,000 times the hydrogen ion concentration. However, when we start to add log into the equation, those differences become smaller. I want you to do a little thought experiment, right? Go back to that pH formula, and I want you to sub in hydrogen ion concentration of 1 times 10 to the power of a negative, 5, and multiply, and also 1 times 10 to the power negative 4. These vary by how much volt, everyone?
10 times.
Yeah, so I want you to tell me, what will be the pH difference? Sub it in very quickly.
1.
1 for which one?
The pH difference would be 1.
Oh, very good. The pH difference would be
yeah.
1. Good. Can anyone tell me the absolute pHs?
Yeah, for the top one, it's 5, and for the bottom one, it's 4.
Okay, very good. Yeah, I guess log 10, you can bring the 5 down. Very good. You don't have to use a calculator. Good. So yeah, I guess the key point I'm trying to make here is a 10-fold change in hydrogen ion concentration represents a 1 unit change in pH. And they love to ask this and test you on this. So just remember that key point. Okay? Very good. And I'm sure you all know pH less than 7 is acidic, pH greater than 7 is basic. So we had a higher hydrogen ion concentration here, and thus a lower pH, as you can all see. Good. Don't worry about this for now. This is just a small little intro into acids, bases, and pH as well, because it does link very closely to the K constant. For questions for you to do in your own time, I would only say question 7 would be good because it's testing the equilibrium point, and maybe question 12 and 11. The rest of it would not be too important. And so now we're on to solution equilibria. I would say students find this, if anything, the most challenging part of Mod 5, and it's not too challenging at all. And it's solely because there is a conceptual element and a calculation element in understanding what happens to salts when they break down in solution. Now, quick question. Why are you learning this? What are the applications of this? Any ideas?
Swimming pools.
Okay, yes, if you work as a pool cleaner, you might be important. I don't know, many of us who would work in the pool industry or as pool cleaners. How about fields that you're all interested in?
Medicine and like
So how might
pharmacy.
it be important in medicine and pharmacy?
Drugs, like they would have the chemical compounds in it, and then that would like, I guess, dissolve in like the acid in your stomach.
Okay, so understanding solubility helps us engineer pharmacotherapies drugs that are soluble in blood, in plasma, or soluble in fat, depending on where we want their mechanism of action to be. That's a very important point. So one example would be aspirin, right? So aspirin is also known as acetylsalicylic acid. We give it to pretty much every single old person with heart problems, which is literally every single old person, right? The way it works is it's a weak acid, and acids, you'll soon learn, are highly soluble in water, right? So it's highly soluble, can be taken via the oral route, for example. So yeah, for medications, that's one use. Does anyone know any ions that are very harmful in excess in the human body? Technically, every ion is, but there is one ion in particular that, if elevated, can cause cardiac arrest, stop the heart, and death. In fact, when a person is dying, one of the major things you think of in the trauma or acute emergency setting is this ion elevated?
Carbon dioxide.
Carbon dioxide is not an ion, it's a covalent molecule, but good logic.
Is it potassium?
Very good. Good. How did you know that, Maya?
That wasn't me.
Oh, who answered potassium?
It was Visa.
Oh, how did you know?
I saw a TikTok on how to kill someone.
Okay, nice. Okay, so social media really helping you all here. Very good. You are right. Potassium. So too much potassium can disrupt ion channels in the heart and cause death. Very good. So I guess ions are very important as well, even when we give fluids. So pretty much every single patient in the ward, I think you've all seen the medical shows where there's a needle inside their vein giving fluids, right? So we need to decide what ions we're going to give them to maintain an isotonic solution, maintain the solubility of, their proteins, plasma, all the other factors, etc. Very good. So you need to understand this for basic human function and just generally for understanding chemicals, polymers, products as well. So let's go through it here. So the basis of ionic compounds. So we'll start with this. Pranav, what are the bonds between ions in an ionic lattice?
Electrostatic.
Very good. So the bonds here are called electrostatic bonds. It's the first thing I want to hear, right? So in an ionic lattice, we have electrostatic bonds between oppositely charged ions. Gerald, why is this called a lattice?
Because it has a repeating pattern.
Yeah, very good. Any organized repeating pattern is termed a lattice, right? Now, in year 11, you learned about different types of compounds, your covalent molecules, your covalent network, your ionic lattices, and your metallic substances. So who can tell me, how strong are these ionic or electrostatic bonds here? So Riyasat, if you had to compare this to covalent network, which bonds are stronger?
I'd say the electrostatic ones are stronger.
Okay, so again, whenever you have a question in chemistry, try having a quick thought experiment. Mithilesh, pick a covalent network substance.
Diamond.
Good, right? And I'll pick an ionic substance. Salt. Which one do you think would be harder to melt?
Diamond.
Have you ever seen melted diamond? I've never seen it, and I'm pretty sure there's no such thing because it has such a high melting boiling point, right? It literally occurs, underground in lava. That's where you see diamond being produced under the high geological forces and pressure. So that should tell you the strongest intramolecular bonds in nature are covalent intramolecular bonds. Does that make sense? Now, does anyone know what the strongest substance on Earth is? It's a covalent network substance. Some of you might have it in your house right now. In fact, some of you might have it in the tip of your pencil right now.
Graphite.
So graphite consists of rings. You might have all learned this. It's an allotrope of carbon. Allotrope meaning same, element, different structure. Do we know what we call each ring of graphite? So when you write, the rings slip off because the rings are bound by very weak covalent intermolecular forces. Inter meaning between molecules. Right? Do we know what we call each ring of graphite? So that is termed graphene, and graphene is the strongest substance or element or allotrope on this planet, stronger than diamond. And I guess this is just so you never ever forget, covalent network substances or covalent intramolecular bonds are the most powerful bonds in nature. So in terms of MPBP, you should be thinking network as number one. Following that, your ionic lattice and your metallic substances are similar. It really depends on what element we're looking at. Okay? Good. And finally, we have covalent molecular substance. Mithilesh, why are covalent molecular substances so low in their melting boiling point?
Because in between them, it's either dispersion or the other forces like dipole, or occasionally the hydrogen bonding.
Very good, right? Because imagine if you have carbon dioxide, CO2, CO2. When you want to melt it, you're not breaking the intramolecular bonds between the carbon and oxygen. You're actually breaking the intermolecular bonds, which are between molecules, which are much, much weaker. Very good. So that was a little bit of recap because you do need to talk about the bonding as well very shortly. And so when an ionic substance dissolves, what needs to happen is water needs to localize around the ions like this, and water needs to bond with and pull the ions apart and overcome the electrostatic force of attraction between the ions. That's what we need. We need to break up this lattice. Now, looking at water, polar or non-polar, Ansh?
Polar?
Good. Which end is negatively charged or has a negative dipole? Dipole meaning a partial charge.
Is it the oxygen side?
Yeah, good. Oxygen is highly electronegative, so it's going to carry more of the electrons, have a slight negative charge. And this is how you represent it. That little squiggly line tells you it's a slight negative charge. It's not a complete ion yet. What are the hydrogens? So they're on the left-hand side of the periodic table, Athava. What can you tell me about their electronegativity?
They have a low electronegativity, and like they're gonna be slightly positive.
Very good. Good job. So if you had a negative ion such as chloride and a positive ion such as sodium, let's talk about the sodium first. Mithilesh, which end of the water molecule would bond to the sodium?
The oxygen.
Very good, right? So this is exactly how you'd represent it. And so which end of the water would then combine with the chloride ions? And let me ask Rabab, which end of water would bind to chloride ions?
The hydrogen?
Yeah, very good, right? So what's going to happen here is we get this kind of bonding. Now, does anyone know what we call this bonding? Now, I want to preface this. If you are ever drawing any diagram about dissolution and you don't mention this bonding, you will lose marks because that is the most important thing you will need to show in these diagrams. What is the name of this bond called? Maybe I'll ask Gerald because you're learning this at school.
Is it ion dipole attractions?
Very good, right? And it makes sense. It's an interaction between an ion, which you see here, and a dipole, which is a slight charge in a polar molecule. Hence why it's called an ion dipole bond. Now, tell me, Gerald, which bond is stronger? The electrostatic bonds of attraction between ions, so the blue lines I've drawn, or the ion dipole bond?
The electrostatic forces.
Very good, right? So they're much, much stronger. So then why do some salts dissolve? If electrostatic bonds in general are much more powerful than a single ion dipole bond, why do salts dissolve in the first place then? Because to dissolve, I told you all, we need to displace this sodium ion, aka overcome the electrostatic bonds through ion dipole interactions. So you can explain that.
So the water molecules, there's not just like one water molecule, there's like many which are like acting on the salt, and that's how like the salt dissolves with the water.
Very good. So I think you can all realize and appreciate this is a model, right? This is not the scale to which things are happening. What actually happens, you think about sodium, right? Sodium is quite large in size. Chlorine or chloride ions are huge, right? I think they've got 17 protons and 17 neutrons, which would make it 35 nucleons in the actual nucleus. Compare that to a hydrogen, which is tiny. So everything's out of scale here. But in reality, what happens is one electrostatic bond can be overcome through thousands or millions of ion dipole bonds from water molecules that are orienting themselves and pulling the ion off the lattice. So you can say cumulatively, a collective number of ion dipole bonds will overcome the electrostatic bonds. And this is only for soluble salts. Okay, very good. So what happens then is as soon as the ion gets displaced, or imagine that sodium gets pulled out of the lattice, what happens next is we form these very organized structures. I'll show you what they look like. This is straight out of your sample answers. You must draw these structures. They're what we call hydration spheres. And what they do is they prevent the ions from recombining back and precipitating out from their soluble state. Okay, so here they've given us an example of potassium chloride. So imagine you've got alternating ions of potassium, chloride, potassium, chloride. The oxygen end of water would have displaced and pulled a potassium out, forming an ion dipole interaction. And as soon as that potassium is removed from the lattice, it will be completely overcome. In fact, I think this diagram is not doing justice. It should look more like this. So if I were to draw it in an exam, I would draw a central potassium, and I draw an oxygen here, oxygen here, oxygen here, oxygen here. Okay, and then I draw all the water molecules like this. Note this does not mean exactly 4 water molecules will surround a potassium. It'll be much more than that, but for model purposes, a simplified diagram, we'll do it in the structure. And so what you'd be showing is this organized arrangement. And I would draw chloride exactly like this. I think that's a perfect diagram. Good. And reset, what do we call these bonds again? These bonds right here.
Ion dipole. So
Very good. Ion dipole bonds. So you need to label that. And you can see here, they've labeled it. And the reason being in the sample answer, that is one essential criteria to getting full marks. And then to improve your answer even more, you can see that these answers have not done it, but you should also draw the lone pairs on the oxygens, right? So they've got 2 lone pairs bent arrangement, and also the dipoles, so negative dipole and positive. That should be negative there. So the oxygen end should have a negative dipole, and the hydrogen end should have a positive like this. And that's it. That's all that needs to happen for dissolution.
So do we have to label the ion dipole bond? Like, you know, when
Yes.
you connected the oxygen with the potassium, do
Yes.
we have to label it?
Yes, you do. Every single time. Whenever you are drawing an ion dipole bond or whenever there is a diagram, you should label it always. I think it's the most important part of these diagrams. Good question. So now you understand why salts dissolve, right? So to break things up, the electrostatic bonds between ions are overcome by ion dipole bonds, and they form hydration spheres that prevent the ions from recoalescing into a lattice. That would be your answer. Now, who can explain why some salts are soluble, some salts are not? What would be your explanation for that? So if your question was, outline why some salts are soluble with reference to ion dipole interactions, what would you mention?
Is it because the electrostatic forces are too great to be overcome by ion dipole attractions? Therefore, only a minimal amount of ions go into solution.
Yeah, very good. So that's exactly the answer, right? So for certain salts, the electrostatic attraction between ions is much stronger, even stronger than collective ion dipole bonds. And hence that salt would never be termed soluble, it would be termed insoluble. Now, I guess the last thing I want you all to understand for a band 6 level of knowledge is every single salt dissolves to some degree. So the question is then, what is the cutoff for a salt being insoluble? Because there's no salt in which not even a single ion will be displaced. There'll always be salts which have varying degrees of solubility. It's like a spectrum, right? It's not a binary of soluble and insoluble. So does anyone know what the cutoff is for defining a substance as insoluble versus soluble? So typically, the cutoff is 1 gram per liter, right? So if less than 1 gram per liter dissolves, we term it insoluble, because that's very negligible solubility. Quite a neat number. It's 1. That's all you have to remember. 1, what's the unit for mass? Grams. What's the unit for volume in chemistry? Liters. So that's quite easy to understand. Okay, very good. So now let's start jumping into it. We've looked at the formulae, and here you can see it's a sample answer explaining how a salt dissolves. So you can have a quick read of this. In this case, they've also referred to entropy. You do not need to refer to entropy. I think this question is referring or asking you to explain the entropy changes when a salt dissolves. I think it would make sense to all of you. If we are disrupting an orderly lattice, what should happen to entropy? Should increase, right? Because they're forming these still relatively organized, but it's much less than the linear pattern of a lattice. So this would be an increase in entropy. Very good. What about enthalpy? What would you say for that, for a salt? Exothermic, endothermic, could be either. What's our answer? Let me ask Athava. What would you say?
I think it would be exothermic because we're like breaking the electrostatic attraction, which would release energy.
Yeah. Okay. Does everyone agree? Any other ideas? Mithilesh, what do you think?
I think since the electrostatic attraction is greater, so you have to put in more energy to break it. So, and then when you form the ion dipole attraction, that gives off less energy. So I think it'll be endothermic.
Good. To be honest, both of you are relatively correct. The answer is it really depends on the salt. So some salts, you are right, can be exothermic, some salts are endothermic. So that's why they'll never ask you a question about enthalpy with salts. But if you were to make a broad generalization, I would say Mithilesh is right in that since we are using energy to overcome the electrostatic bonds, then that's a significant amount of energy that could be termed endothermic. But there are salts that are exothermic as well, so don't remember an enthalpy change. Entropy always will increase though. Good, very good, good job. Let's move on. So again, these additional HSC questions you can do in your own time. So this is how they'll test you. You can see, draw a label diagram of the dissociation of sodium chloride. What I would draw is I would draw on the left the sodium chloride lattice and the ion dipole bonds beginning to form. And on the right, I would draw an arrow and draw the hydration spheres for sodium and chloride. And that'd get you 4 marks. Okay? You just need to mention the ion dipole bonds. That's the most important thing. Not too hard. Okay, now solubility table. So there is a smart way to learn this, and there is a complex way to learn this. The smart way for now, for all of you to learn this, is remember the rule of thumb, and then use your data sheet as a little hack. Okay, you should eventually memorize a solubility table. I'm not going to force it on you in one single lesson. Okay. Now, when it comes to the solubility table, the way I understand this is I break it up based on anion, okay? Not cation. I look based on anion, so that's how I have categories. Now, before we even jump into every single ion, there is one ultimate rule you cannot forget, right? And if you forget this rule, then you definitely can make silly mistakes. And that is every single salt that is derived from a cation that has a +1 charge. So all group 1 metals. And what's the polyatomic ion that we just went through that had a +1 charge, Rabab? Do you remember? There's one polyatomic ion.
Ammonia.
Ammonium. Very good.
Ammonium.
So all group 1 metals plus ammonium salts are always soluble. You can never forget that, right? So that's the first thing. Whenever I draw salt in front of you, you should ask yourself, is that a group 1 metal or ammonium? If it is always going to be soluble regardless of the anion. That is rule number 1 of solubility. Does that make sense? Write that down in red, highlight it. Group 1 metals, write it clearer for you all. Group 1 metals and ammonium salts are always soluble, regardless. Always soluble. Very good. Does that make sense so far? Okay. The next thing I do is I break it into little classes. So there are soluble anions and they're insoluble anions. Now, before I teach this to you, let me ask you all. If I gave you something like this, right? Let's say you did not know. Let's say you're sitting your HC exam, you had no clue if this is soluble or not. I'll draw the actual, so it's BMG3, PO42. You've forgotten your solubility table. It's the day of the HC exams and you've been asked to use its solubility somehow in a calculation question. What would you do now to determine whether it's soluble or not? Who can tell me? A bit of a challenge question. Those of you who have learnt solubility product should start to be thinking of how to do this. Give you a hint. Open your data sheet. All of you should be looking through your data sheet. Tell me where magnesium phosphate, if it does pop up, is in your data sheet. And where is it present in your data sheet?
It's in the second column, like in the middle-ish.
Good, but what's the title of that section of the data sheet? What does it say? It should say KSP values. Does it say that?
Yeah.
Good. So this is your little shortcut to learn things smart. If that salt is listed in that data sheet, it is insoluble. So you have only been given KSP values for the insoluble salts in your data sheet. Does that make sense? Okay, so every single salt that you see there is insoluble. So if you're stuck and you really need to check, go back to that data sheet and it'll tell you if it's there, it's going to be solid. Okay, very good. So that's just a little shortcut to think about things. But let's say you are good and you remember the solubility table. So generally, the way I remember things, how do you all remember huge pieces of information? Because this will be very important and a bit of a hack for you, especially later on in life as well. Even in the HSC, what can you use to memorize big pieces of information? So those of you interested in medical school, when you get to 50 or 60 year exams, you'll have to know 10 different side effects for hundreds of different medications that all have the fanciest names. So how do you remember all of that stuff?
Flashcards.
Yeah, yes, we use Anki, which is a flashcard system. I would say acronyms and using visual stories. I think you have to realize your brain is very, very powerful, right? No computer can, in fact, even match all the neural connections and synapses, right? I guess to break it down, if someone were to have a stroke, which is where there's a blockage in the brain, each minute they lose 7 kilometers worth of connections between brain cells. So you can imagine how many connections there are in total if every minute you're losing 7 kilometers worth of connections, right? So to break it down here, your brain is very powerful, specifically the visual part of your brain. So I use stories to remember a lot of these information. So I'll help you out here. Now, your acetates and your nitrates, they are always soluble. Always soluble. Okay, acetates and nitrates, you just get used to that. They are always soluble. And so that will take us to our partially, soluble anions. So here we have your chlorides. And also other halogens as well. You can think of your iodides, your bromides, but your chlorides are your main ones that you'll be dealing with. Now, the little story I imagine in my head is that I imagine we are on planet Mercury, Okay, so you need to really close your eyes and imagine this, and that's what will solidify the information. So really think about this. You're on planet Mercury, it looks like Mars, orange surface, and on planet Mercury, I imagine that there's a silver lake, shiny silver lake. Hopefully you've all seen liquid silver. It's like pure reflective, like the Silver Surfer, if anyone's seen the Marvel movies. And if you reach down into the silver lake, I want you to imagine that you pick up a lead pencil. Right, your favorite lead pencil could be your lucky pencil from that silver lake. Now, from that story, you've been told 3 metals. What were the 3 metals that you remember now?
Mercury, silver, and lead.
Good, right? Mercury, silver, and lead. And some people add strontium as well, but we're not going to because you will never, ever, ever, in my past 6 years, I've never seen a question on strontium. So don't waste your brain space. Silver, lead, mercury are the insoluble exceptions to chloride. Okay, very good. Now for sulfates, what I remember, sulfates are your next ion. I literally copy paste this trio and I bring it down. So it's the same 3 elements. Silver, lead, mercury are also insoluble for your sulfates. So whatever's insoluble for chlorides is also insoluble for sulfates. And the only addition here is we add 2 ions that are very similar to one another. I think of the twins. These are 2 ions that almost look like twins. And it's your calcium. And what other element is very similar? So it's the exact same charge and also ends in A.
Barium.
Good, barium. Good job, right? So calcium and barium are the additional insoluble exceptions here. Again, everyone, I'm not expecting you to memorize this all in one lesson, but by the end of year 12, you should generally have this in your head. Okay, good. With your insoluble anions, does anyone know any insoluble anions before I take you through that? What are some ions where you look at, the second you look at this anion, you think, okay, it's probably insoluble?
Carbonate.
Very good. I remember it's the ions with, huge negative charges, right? So the huge polyatomic ions. So your phosphate is the one I'm really, or most of the time will be insoluble. Also your carbonates. And then also your hydroxides. So that would be the last one I'm concerned about. What would be the exceptions here? So, Athava, what was rule number 1 of solubility?
All group 1 metals, so they would all be soluble. Yeah.
Good. So the exceptions for phosphates and carbonates is group 1 and ammonium. And then for hydroxide, I literally just copy paste those 2 twins. So now those 2 ions are soluble exceptions. So for hydroxide, it's group 1 metals and ammonium. But calcium and barium hydroxide are soluble exceptions to your insoluble anions. That's it. That's the solubility table. So again, this is an information overload, so I don't expect you to memorize it just yet. Just look at it here and there. Maybe, print out a solubility table and put it on your... I wouldn't even say that's important. Don't worry about that just yet. Just write this down, and hopefully you have a general understanding now of which ions are soluble and which ions are not. I want you to start thinking about this now. Good. Have we written it all down? Happy to move on? Good. All right. So this is exactly what I mentioned to you, right? So for insoluble, we say typically less than a gram, you would start to see that solubility starts to decline. So you could technically call these 2 categories insoluble. So if it's less than a gram per liter. However, this is clearly insoluble, right? So those are just crude cutoffs, but remember 1 gram per liter is a cutoff to be soluble. What's the trend we're noticing here? Let me ask Tanisha, what's the trend you see here?
The things with like NO3 are up at the top, like they're rising really fast, I guess. And then, yeah, That's kind
So
of
what I would do is,
weird.
if given a graph, I'd start even broader than that, right? What's the general trend in all of these lines before going into specific ions, right? So orient yourself. This is solubility with temperature. So as temperature increases, what is happening generally to solubility? Increasing, right? Good. Now the second point is, so as temperature goes up, the solubility is increasing. And then you can start looking at specific trends, right? And then you can look, okay, nitrate salts have a higher solubility at a particular temperature. All of that's not too important. What does that tell you about the enthalpy of most salts? Increasing temperature increases solubility. Let's write the equation for the dissolution of a salt. How about we do that, right? So let's pick a salt. I'd get Ansh, pick any salt here that goes up.
Calcium chloride.
Okay. So the way you would write in year 12, the way you write the ionization of a salt is you write the solid salt on the left-hand side, the calcium chloride, and then you would draw an equilibrium arrow, and then you would draw calcium, and then chloride ions. And the reason we draw equilibrium arrows, everyone, is sometimes it might not be equilibrium. Sometimes all of the salt will dissolve, right? But this is specifically for the insoluble salts. What did we say? Even when a salt is insoluble, some of it will be in aqueous state. Remember we mentioned that? It doesn't mean that every single molecule is solid state. So for insoluble salts, we would typically write an equilibrium arrow. Does that make sense? Good. So calcium chloride, that would be that should be a soluble one, but for this purpose, let me change this to lead chloride. I think you'd all know lead chloride. Lead was an exception to chlorides. Remember, chloride is a soluble salt. Okay, and I'll change the right-hand side to lead as well. Okay, so what does it mean if increasing temperature results in shifting to the right-hand side?
All
reaction is
reactions endothermic.
Yeah, very good, right? And see, this proves Mithileish's initial point that most salts would be endothermic, but then you can also see exceptions here, like these fancy salts that follow a typical exothermic pattern. So again, it does depend, but rule of thumb, you could say a lot of them are endothermic. So we're going to favor the side that decreases temperature and shifts to the right-hand side. So I guess the conclusion you would make in an exam, if you saw a graph like this, is most salts are endothermic. That'd probably be the most difficult conclusion to make. And that solubility increases. In general, solubility increases with increasing temperature. Good. Let's move on. Okay. I guess before we go to our calculation question, before I teach you KSP and breaking down KSP calculation questions, you are required to know this dot point. This is one of those dot points which is, you know, just put there because you're learning it in the Australian syllabus. So they have to link it to some kind of Indigenous or Australian, pharmacotherapy or plant, etc., right? And so what this dot point is trying to get you to understand is how even the Aboriginal, Indigenous, Torres Strait Islander people used solubility knowledge even prior to understanding equilibria, right? So what you see here is a cycad, which is a palm-like plant. And you can see that the seeds in those cones right there, that's what they used to eat. So they used to cook it, boil it, eat it, for example, right, for nutritional value. However, the cycad seeds contain a toxin known as cycasin. Cycasin. You don't need to know its chemical formula. This is what it looks like. It's a pretty funky looking organic molecule. It's got a bunch of carbons. So every single edge you see here, this, every edge is a carbon. So that's how you understand these graphs, these skeletal diagrams, right? You just know it's an organic compound. So key point here is cycads contain, the seeds contain the toxin cycasin. So indigenous people used to eat cycad seeds without getting the symptoms of poisoning. Now I want you to think about what you would do, right? I'm going to give you a few properties of Cycasin, and I want you to tell me what you could do to detoxify this food source. So one of the key properties here is that it is very highly soluble, right? Maybe you can just remember as a rule of thumb, solubility is even greater than 50 grams in a liter. So what could we do to detoxify cycad seeds if we were to consume them?
Put it in running water.
Yeah, very good. So one of the key principles to removing cycasin is number one here. We call it leaching. Let me take you to it. So point one, leaching. Now, why running water? So typically what they did was they put it in some kind of woven basket that had a lot of pores as such. And the seeds would be in those baskets and they'd be in running water. Why running water? So I think Athava, you mentioned it. So why running water?
So like it doesn't stay in the basket, it like gets washed out and like it moves it away. So and then more fresh water can come in, and if there's any left, it will get rid of more acid.
Good. See, this is the thing. Most people understand the principles, especially with the stop point, but it's about getting full marks here. I'm still looking for a few words which I want to hear in your answer beyond what was mentioned. What else would you mention?
If the water stays in the basket and there's no way for it to go out, the reverse reaction would occur.
How about I simplify it and help you all out? You are right, but I want a little bit more detail with buzzwords. You're all implying it, right? So what's happening here is cycasin can become aqueous. Okay. Now, if we put it in running water, what is the stimulus that we are applying to the equilibrium? You need to apply it in terms of what you're learning, right? So explain it in terms of the Chatelier's principle. That's what I'm looking for. So what's the stimulus when you run it through running water?
The concentration decreases.
Of what? This is where
The cycasin concentration decreases.
Even more specific.
The volume increases.
Oop. Who can explain it? Close.
The solid cycasin concentration decreases.
Are you sure solid cycasin? I know the basket is woven, but it does not allow the seeds to be removed.
Yeah.
What could you all say?
The aqueous cycasin concentration decreases.
Yes, it's very tiny. I'm being nitpicky because if you say the wrong thing, it is wrong. So if you say solid cycasin concentration decreases, you would lose a mark. Or if you just say cycasin concentration decreases, it does not make sense. You would not get a mark as well. So you need to mention using running water, you are constantly removing aqueous cycasin toxin, right? So aqueous cycasin toxin decreases. So what's the opposite of this? You want to increase aqueous cycasin. And as a result, which direction will we go? Right-hand side. And thus, what is that going to do to the amount of solid cycasin left in the seeds?
Decrease.
Yeah, therefore decrease solid cycasin. Or you can say, therefore decrease cycasin in the seeds. That'd be cycasin in seed. So that is how you would explain leaching. If you're ever given a question like this, if you start explaining it very basically without referencing LCP, you will lose marks. So that's what I'm trying to point at here, right? So an exemplar answer would be, one method the indigenous people used was leaching to minimize toxicity of the cycad and cycasin in seeds. This was done by placing seeds in a woven basket in running water. This constantly removed aqueous cycasin and thus shifted the equilibrium to the right to counteract this change. As a result, cycasin concentrations in the seeds was lower and able to be consumed. Does that make sense? See how I mentioned LCP, I mentioned the technique, I mentioned the toxin. Good. So literally, everyone, if you have a template answer to this question, you will always get full marks. Very easy. Okay? Good. Let's talk about one more method, right? It's an organic compound. What else can we do? Think about what do we do to meat, right? Meat has a lot of bacteria, salmonella, campylobacter. You eat meat directly, you will get severe bloody, diarrhea, gastroenteritis. So what can we do to inactivate the toxins?
Do you add energy to break the bond?
Heat, yeah, very good. So you can use heat to denature cycasin. So that's one thing you can do, right? That's what we do for animal foods as well. Good. Who likes sushi? No one? Yeah? Okay. Well, how can we eat sushi if it's raw? We just risk it?
Doesn't sushi grade fish get flash frozen on the boat?
Very good. It gets frozen for a long period of time. That can result in dormancy. But the con there is there'll always be parasitic eggs inside the fish as well, right? Because you actually haven't denatured or cooked it at high heat. So whenever you eat salmon or sushi, you do eat some level of, parasites, etc. But you'll likely not get infection because they'll all be dormant. Yeah. So I guess the definitive management here is we would have to heat the cycad and the cycad seeds to denature the toxins. So that's one other way. There's one last way, and it's burying the seeds. Now, it sounds a bit nasty. Why would you bury seeds? Because it'd get broken down. But that's precisely the point. When we bury something, we can ferment the chemicals. And so we can actually ferment the cycasin because it gets acted on by bacterial and fungal enzymes to inactive metabolites. And so those are the three main ways that the indigenous people kind of neutralize cycasin for consumption. It's all written here. Okay, so cooking the seeds, leaching them, and leaching is the most important one. And you can see how I've explained it, everyone. I would even go as far as to include a general equation like this. Kind of like how we did, even that would suffice. Some kind of basic equation to show the equilibrium shifting. And the final thing we said was fermentation. And with fermentation, you need to mention it's broken down by enzymes. Good. What about for temperature? What do you think you need to mention for cooking the seeds? Remember, you need to link this all to properties. Let's go back up here, right? Investigate the use of solubility equilibria when removing toxicity from foods. You need to reference properties. This isn't a history class, it's a chemistry class. So what do you want to mention?
It breaks the bonds, the intramolecular bonds.
I would just say at 150 degrees, we'd start to get decomposition of cycasin, right? So yeah, you could say it starts to decompose intramolecular bonds as well, because you need to change the chemical, right? So you are right, it would be intramolecular. Good. So that would be the things I would remember. So it's got a high solubility, about 50 grams per liter. It's got a lower temperature, so it can be heated to denature the toxins, and finally fermentation. If it was a huge long response, what would you mention for enzymes? What are they?
Catalysts.
Which lower the activation energy for decomposition reactions, right? Do you see how we're linking this back to chemistry? That's what you need to get good at. And that's it. So here I've given you literally a template question they'll ask. If they were to ask you anything, it's going to be this question. They can't vary it, everyone. If anything, they'll give you a graph of cycasin solubility over time or temperature, and then you'd have to use the graph to explain whatever we just learned, which is not hard at all. Good. Do these questions in your own time. Have a look at how easy the questions are once you understand it. So this is question 3 from 2019 exam choice. You'll have 20 seconds to answer this question. So raise your hand once you've got an answer. Good, right? Literally copy paste, sure. So what's the answer, Rabab? A, B, C, or D?
C.
Very good, yeah, that's it, right? I didn't mention anything about reactivity with water. It's all about solubility. Density is not too important, and it's not immiscible. Immiscible means insoluble. Very good. All right, are we ready to start doing some actual calculation questions? This is a high yield part of solution equilibria. Everything you've learned until now, quite low yield. In fact, I don't even commonly see the ion dipole hydration sphere questions being asked much. I think they were asked maybe once in one of the past HSC papers. They rarely get asked in trials. These questions, I can almost guarantee every single trial paper they will pop up. In the HSC, I can guarantee they will pop up. So very high yield for the rest of this module that you put 100% focus. Now, we've hit an hour. So what we might do is we'll take a 5-minute break, go stretch, stand, get some water. And when we come back, we'll go through the calculation side of solution equilibria. So I'm going to take you through determining solubility, converting solubility into different units like percentage weight per volume, grams per liter, and then finally, if we have time, we'll go through common ion effect, and that would mean we finish the entire module, which is very, very fast, but also very, very good. Okay, I think we'll probably finish next lesson though, not this lesson. Okay, so get some water, and I'll see you all in 5 minutes. Okay, when we're all back, it'd be great if we could turn on our cameras again. We'll start going through it. Good. And Athava, Ansh, Tanisha, Pranav, are we back? Good.
Yeah, I'm back. I'm just eating lunch, so I won't turn on my camera.
Okay, good. I think we'll start now. I think everyone is back. All right, so I guess when we're doing calculation questions, it's the exact same principles, right? It's write your equation, then write your data. Now, whenever you're writing your equations, this is just a small point, but it will help you so much. Make sure the solid is always on the left-hand side, and make sure your ions are always on the right-hand side. So do not write it the other way. And the reason is, when you find the K constant for these questions, which is what you're going to be doing, right? Finding what we call the solubility product, you'll have to find the concentration of ions A plus and B minus. Or if you were to do it the other way, you'd get 1 on A plus and B minus. That's not wrong. You can do it the other way, but it would make your calculations much more difficult, and you'd actually get different K values. So you'd indefinitely get the question wrong as well. So make sure your ions are always on the right-hand side. That is my first tip. Now let's talk about these 3 terms before we mention any calculations, and that is unsaturated, saturated, and supersaturated. What do these 3 terms mean to you all? Because we can only use the K constant or find the K constant in one of these scenarios. Gerald, do you want to give it a go as you're learning solution equilibria?
Yeah, so for an unsaturated solution, that means that all ionic compound has gone into solution, but there is still ability for the solution to dissolve the compound.
Good.
Saturated is when the solution can no longer dissolve an ionic compound in that.
Good. And I'll ask a broad question to all of us. When a solution is saturated, Gerald has mentioned, we have the maximum amount of solute in solution. So when it's unsaturated, it has a sub-maximal amount of solute in solution. So all of the solute has dissolved. That's what it means when it is unsaturated. All the solute has dissolved, and there is capacity to dissolve even more solute. When it is saturated, we say that the maximum amount of solute has dissolved in a solvent at a given temperature. Temperature is important because what happens to solubility with temperature? It generally increases. Do you all agree? So you need to mention solubility in terms of temperature. So always finish it off with at a given temperature. So my question to all of you, and this is what students notoriously find hard, because they're going to cue you to this. They're never going to tell you this is a saturated solution in a hard question. they'll cue you into it. And they'll cue you by telling you whether a precipitate is there or not. So if a solution is saturated, should there be any precipitate?
Yes.
No. Okay, so Gerald says yes, Mithilesh says no. What do we think? Riyasat, what are you thinking? When it's saturated, the max amount of solute has dissolved in a solvent at a given temperature.
I think yes.
Okay. Athaba?
I think no, because it says a max amount of solid has been dissolved already. So if you add any more, then it will be precipitated.
Very good. Okay, so the answer is, in theory, you should not see any precipitate. But in exam questions, everyone, they will cue you using this buzzword, faint precipitate. If they ever tell you that there is a faint precipitate, or there is a very light precipitate or anything of that sort, they're telling you the solution is saturated. Does that make sense? Now, only when a solution is saturated can you use KSP. There is no other scenario where you can use KSP. If it's unsaturated, we call it Q, just like how we did when we referenced an equation that's not at equilibrium, right? Now, SP, as I told you all, is solubility product, and it just refers to solutions of salts, right? So when it is unsaturated, we call it Q. And in this case, we'd say Q is less than K. That makes sense, right? We still haven't reached equilibrium yet. The forward reaction is still going to be favored, or more ions can still dissolve. Now, what would it mean if the solution is supersaturated? Would I see a precipitate now? Pranav?
Yeah.
Good, right? So I would see a precipitate. So it's a precipitate is formed. And Pranav, what would we call the equilibrium constant at this point? Would we call it K or Q?
You would still call it Q, yeah?
Very good. And is Q greater than or equal to or less than K?
Greater.
Good. Now I'm just going to add one level of detail here, everyone. When we refer to Q, or the reaction quotient, when it comes to ions, we call it the ionic product, or you might see the word IP written next to Q. So again, Q, we now use slightly different words, and this is just in your exams, you will see these words being written. So Q is called the ionic product. K is your solubility product. And if you forget everything else here, remember, you can only ever use K when a solution is saturated. And the way they'll cue you to this is they'll tell you it's saturated, or they'll tell you there is a faint precipitate. Faint precipitate. Does that make sense so far? Any questions as of yet before we jump into things? All right, very good. It's the exact same principles otherwise, right? So let's try this question here. So they've told you that you've got barium hydroxide at 25 degrees, and they've given you its KSP. The typical question they'll ask you next is to calculate the concentration of barium and hydroxide ions in solution. And this is teaching you something that's very, very integral to your approach in calculation questions. And that is, whenever you have K, you can find concentrations. Whenever you have concentrations, you can find K. That's always been the case, right? It was rice tables for your, your previous questions. You did rice tables, found concentration, you used it to find K. However, now, I want you all to realize something very important. You don't need to do rice tables in solution equilibria. And the reason is, it's usually quite simple. Can anyone tell me why we might not need to do rice tables? There's no harm in doing it. If you're stuck, confused, by all means do it. But what makes salt dissolution unique in that there's not really much point in doing a rice table?
Is it because there's only like two factors and there's no fractions and it's like just simple to calculate it?
There are ratios here, you can see that. The reason is, everyone, there's not two reactants, right? So not even the two reactants, but they haven't given you, they can't give you two different levels of ions. They'll always give you a starting amount of the solid, which doesn't matter, because remember, this is a solid, we don't even account for it, right? So the initial concentration of your ions is always going to be 0, and it's always going to increase by the stoichiometric ratio. That is the Rice table. Does that make sense? So basically, there's no point doing a Rice table in these questions because the reactant is always solid, aka not included in K. And these two products always occur according to the stoichiometric ratio. And they're always 0 initially. So there's no point doing a Rice table. So to do this question, let's do it together. In fact, I'll give you 30 seconds to do it yourselves without a Rice table. Remember, solution equilibria, there's no need to do a Rice table. So jump straight into it. You tell me what hydroxide concentrations and barium concentrations are. So raise your hand as soon as you get it. Should be done in about 30 seconds or so. Good. All right, I'm going to start going through it. So again, same principles here. Write your equation first. Second, you write your data. You haven't been given much data except that KSP is equal to 2.55 times 10 to the power negative 4. Now I have a question for all of you. Ansh, when I find the concentrations, what concentrations am I finding? Am I finding the concentrations in an unsaturated solution, saturated solution, or a supersaturated solution?
A saturated solution, since you give
Very
it KSP.
Yeah, very good, right? Because since we're using KSP, it has to be a saturated solution. So what you're actually finding, another way they can word this question to make it sound harder is they'll ask you, what is the maximum concentration of barium or hydroxide that can dissolve at this temperature? And the answer is, it's whatever concentrations you find using KSP. Those are the max ion concentrations. So then all we'd have to do now is we find KSP and we say the expression is equal to we would have written this. Now what we need to do now is we let the solid be equal to X, right? We assume X amount of solid has dissolved in concentration. What that would mean is we produce X moles per liter of barium and 2X moles per liter of hydroxide. Does everyone agree? So then we simply sub that into our equation. Well, KSP we said is equal to barium times hydroxide squared. So we're going to say that equals to X times 2x squared. What do you notice here? Whenever you square something or root it, it's also equal to the number inside the bracket. Does everyone notice that? Now, a small error check for all of you. Whenever you are doing this step, just have a quick check if the number inside the bracket is the same as the number outside the bracket, right? If that's the case, you are on the right track. If you haven't done that, you may have made a silly mistake. Good. So we can therefore say that 4x cubed equals to 2.55 times 10 to the power negative 4. What's x equal to? What did you get, Mithilesh?
I got 0.04 moles per liter.
0.04 moles per liter. Okay. So that's equal to the concentration of barium. What about hydroxide?
0.08 moles per liter.
Good. And how many sig figs?
Yeah, I didn't really do sig figs, but I should have.
Good. So what would you do now if now you know that sig figs should be done? How many sig figs would this be to?
3.
Good. So if it was to 3 sig figs, does anyone have our answer to 3 sig figs?
0.799. 0.0799.
Good. And what about barium?
0.0399.
Okay, good. All right, let's move on. Oh, that's... Oh, we can do this question. We'll do that one later. Trying to find a good question for all of you. Okay, good. So this is the inverse, right? So what we just did just then was we used KSP to find concentrations. Does that make sense to all of us? Now, the title for this question is going to be concentrations to KSP. I'm not going to say anything. I want you to do question 4A yourself. Use the knowledge that we just used to answer question 4A. This is, I don't know which paper it's from, I believe probably just from HC Additional Questions. Again, when you get your answer, raise your hand. Mahe, you'll take me through this one when you're ready.
Okay.
Okay, we're going to start going through this. So Mahe, can you start us off here? What do we do? What's the first thing you would always do in any calculation question?
Write the equation.
Yeah, right. Step one is always equation, data, and if you're stuck, find moles, right? So what equation are you writing? Tell me what it looks like.
CaOH2.
Yep.
Double arrow. Ca2 plus
Yep.
2OH minus.
Good. Aqueous on the right, sulfate on the left. Good job. All right. What do I do next?
Okay, then we can find the KSP value from the table for calcium hydroxide.
One important point Mahi has mentioned here is sometimes they won't give you you can't directly get KSP from the data sheet, but I think he's mentioned a very important point, which is sometimes you'll have to use KSP in the question to calculate something else, and they will not give you the value because it will be in your data sheet. Just remember, every single insoluble salt that you can be asked, its KSP will already be given to you in the data sheet. So keep that ready and open in case you need to use it. And always in a solubility question, just write it down on the side. Okay, so Mahe, do we have the KSP for the salt from our data sheet?
Yeah, I think we do. 5.02 times 10 to the power minus 6.
Okay, now we know we're not going to use this because the question is asking us to calculate it from this data, but I think we can just jot it down there just as good practice for ourselves, okay? So again, we're not going to use that value. All right, let's continue. What other data do we have, Maya?
So we also have, well, we can write the KSP
Expression.
equation, I guess. Yeah, expression, sorry.
Now, before you do that, I want data. So before you touch any formulae, you always need to give me data first. So tell me what's V, what's M, What's T? What do we have?
So we have the number of moles of calcium hydroxide.
Do we have the number of moles?
Sorry,
of calcium?
concentration.
Do we have concentration? I would say we've got V. And what else do we have? Give me letters. I don't want words.
M. So
Good. So
0.173.
M's not a concentration, it's a mass, right? But you're right, we can find concentration. But let's get the raw data out first. So we've got mass, we've got volume. So M and V, we've got T. Mithilesh, why have they given us T?
Because the value of K changes at different temperatures.
Very good. So that's the only reason they're giving it to you, right? Your solubility will also change based on temperature. Very good. So we've got an M, we've got a V. What can we do now? So remember, if you're stuck, what do you find? N, right? But I think you all know, if you've got an M and a V, you're going to convert the M to an N and find concentration. Because remember, to get K, you need concentrations. To get concentrations, you need K. You need to remember that very intimate link. K, concentrations, concentrations, K. So what's our number of moles of calcium hydroxide? So I'll get a Rabab. What did you get for your number of moles of calcium hydroxide?
Just a second.
Yeah. Tanisha, have you got one?
It would be 0.173 because you've put oh wait.
100 ml is 0.1.
Yeah. So it would become
The 1.73, everyone? Is that what we've got for our moles?
Yeah, that's what I got.
Oh, sorry. No. I'm making a mistake here. It's your mass divided by molar mass. I don't know what we're doing. So your mass is 0.173. You need to divide it by the molar mass, right? So what's the molar mass of calcium hydroxide? I don't care what the molar mass of calcium hydroxide is. Can someone tell me what the number of moles is? So 0.173 divided by the molar mass of calcium hydroxide.
Yeah, okay. I got 173.
173.
Fraction.
173? Yeah.
Divided by 74,096.
Okay, let's give me a decimal point and we'll store it. How about that?
0.00233.
0.0023, yep. And you can do ... store it as A. So that's what you'd write in your paper, right? Don't worry about fractions. Fractions can become confusing. Just do it to a couple decimal points and show them that you've stored the answer. Good, so we'll store it as A. Now we've got our N, we've got a V. Can we find C?
Yeah.
Good, so we're at C equals N on V. Now, small practice, everyone. Make sure you always put the formula before subbing. In the HSC, they can take marks off if you don't include the formula. It will be for specific questions that you're not aware of. So build that good practice now. C equals N on V. So what's our C? So that's A divided by 0.1. What do we get? So I'll get Riasat. What do you get for concentration of calcium hydroxide?
Uh, 0.023, and it just continues.
Okay, we'll store that as B. 0.023 ... store it as B. Okay, so now we've got our concentration. What can we do now? So we know the concentration of calcium hydroxide is B. Can we do anything else now? Well, what are we trying to find? We should probably frame our question. We're trying to find K. I always like to write K SP equals question mark, so I know what I'm trying to find, so I don't, go off on a tangent. What's the expression for KSP? Is it not calcium ions multiplied by hydroxide ions squared? Everyone with me? So what are we going to sub now for our calcium ion concentration?
0.023.
Yeah, very good. So we can say if there's B moles per liter of calcium hydroxide, the concentration of calcium is B, concentration of hydroxide is 2B, because there is double the hydroxide as calcium. So then when you start subbing it in, you'll get B times 2B squared. Do you start seeing why whenever the number's outside is greater than 1, the number inside the bracket should also be the exact same. So just double check that. And that's most of the time. There are exceptions when we get there, but good. What do we get as our answer now?
5.09 times 10 to the power of -5.
Good, right? 5.09 times 10 to the power of -5. How many sig figs for this question?
3 or 2.
3 or 2, are you sure?
No, not 2, because we don't use the temperature anyway, so probably 1 then.
Good, yeah. I think we've used the 100 ml, right? Because we said that's 0.1 liters here. So I'd say that rounds off to 1 sig fig. So 5 times 10 to the power of -5. Yeah, and we're at 1 sig fig. Good, and that'd be full marks. So I guess these questions are very easy because as soon as you want to find K, you need to find concentration in moles per liter. As soon as you want to find concentration, you will be using K. So just remember this link. To find K, you need concentrations. To find concentrations, you need K. So very easy, these kinds of questions so far. We'll get to a slightly more challenging ones now. You can do question 5 in your own time. This is a graphing question and explaining that. And let's go to, let's start doing some exam questions. How about that? Shall I give you all a hard question? Let's see. Okay, we'll do one more of this question, and then I'm going to throw you in the deep end. This is going to be a final warm-up, and then you will go to a slightly different question after this. So you can maybe write this as, this is question, which paper is this? 2019 Independent. Question 9. So now focus on speed. I think you all know how to do these questions now. Just to build that repetition and practice, focus on how fast you can do it. See who can answer this the fastest. Good. Good job. I'll give everyone about 10 more seconds. Good job. Okay, I will get Athava. Take me through this question. What should I do?
Write out the general equations first.
Good. So like you've got good first practices. Good. So solid, aqueous, lead, then 2Br minus. Okay. So I've written my equation. What do I do now?
And then you write the equation for K, which is let one of them be X. So it'll be X times that, and then it'll be X times 2X squared in brackets.
Yeah, so we can say let this be equal to X. Remember how I always put I always do this at the top? I would advise you all to do the same thing. So it's like a shortcut rice table. So I let the concentration equal to X. That would mean this is also X. That would mean this is 2X, right?
Yeah.
So then this is equal to X times 2X squared.
Which
So
then that equals to 4X cubed.
good.
And then we know that is equal to 6.6 times 10 to the minus 6. So you divide by 4 and then cube root it. And then you get B.
Good.
Right. Yeah.
Does everyone get B?
Wait, no B. I mean C.
C? Did everyone get C?
Okay.
Good. Okay, so 0.012 moles. Good. So quite easy now. I think you're all getting the principles here. Very good. All right, maybe I might throw you into harder one, but I want to see. Okay. BII. Slight variation of a question. Again, I'm not going to say anything. Shouldn't be too challenging, but I'm going to give you all about 4 minutes or so. Maybe I'll give you 2 minutes and then I'll start taking you through it, okay? So start your approach. I want every single one of you to have some plan of attack. Good. No rush for this question. 2 minutes and then I'll go through it with you. Okay, get some water. I'll be right back. Okay. Anyone got an answer?
I got no precipitates formed, but I'm not too sure.
Okay, sure. We'll go through this. Let's do this. Has anyone else got an answer? Okay, don't worry. I put you all in the deep end. But again, in your HC exam, I want you all to realize there'll always be at least one question where everyone would have never seen before and would have to apply what they know to this question. So it would be this level of difficulty as this question is to you right now. So I want you to eventually get to the stage where even if I do put you in the deep end, you can work from first principles to get to this. So let's go through this question. Now, again, before we delve into calculations, what are the first 2 things we always do, Pranav?
Chemical equation and then data.
Good. Now, Pranav, can you tell me what equations you've written?
I've written the
What do you
sodium
have?
sulfate. Okay, so Na2SO4 gives 2Na plus SO4 2 minus. And then I've written down the barium nitrate as well.
Okay, pause for a moment. You said 2SO4 plus Na plus? I would say let's start by writing the full equation, right? So you've got your Na2SO4 plus your BaNO3 2 gives you what else do we have? We've got a BaSO4. We've got NaNO3. And if I were to balance this, it should be a 2 here. So who can tell me which one of these is solid? If all of them are aqueous, there's no reaction, right? So which one of these products is solid? The BaSO4 and NaNO3. Apply your basic solubility rules that you just learned.
BaSO4 solid.
Yeah, right. Remember your sulfates. Everything is soluble except for, what were the exceptions? I'm just going to ask random people. You're going to tell me one exception. Tanisha, what's one exception for sulfates?
For sulfates, it has to be
Lead pencil, mercury, silver lake.
yeah.
So lead, silver, mercury, right? Reset, give me one more.
Calcium.
Good. Calcium, and then we've got barium written right here. Very good. So your sulfates are all soluble except for the ones that we've just mentioned here. Good. Everything else is aqueous. So what does that mean for the sodium? And what does that mean for the nitrate if it's aqueous on the left-hand side and the right-hand side? Because we want to find a net ionic equation, right? So, Jared, what am I going to do to those ions in a net ionic equation?
You can remove them because they're spectator ions.
Very good, right? So we get rid of them, get rid of that, get rid of that. So the key reaction here is Ba2 plus SO4 2 minus gives me BaSO4. That's what you should have written at the top to get 4 marks, okay? I told you to skip it, but again, the reason you have parts to a question is not to make it harder, everyone, it's to help you. When they give you part A, part B, part C, they're all meant to guide you to the final answer. So if you were stuck, I would have gone back to part I. Good. So we've got our first equation. I'd say this is the important equation. Would we like to rewrite this in any other way? Remember the little tip I gave you. Where do you want the ions to be sitting? Left or the right-hand side?
To the right.
Good, right? Otherwise, your K constant is going to be all funky. So we're going to rewrite this as Ba2 plus and SO4 2 minus. Good. What do I do next? We'll get Mahe. What do I do next?
So we can write out the information that we have.
Good. So what data do we have? I want letters. I don't want concentration, volume. I want C, V, N.
Okay. So
Give me
C Na2SO4 equals to 0.02 moles.
Yeah, let's just double check. Yep, good. So C of Na2SO4 is equal to 0.02 moles. Okay, let's take it a step further, Mythflesh. What's the concentration of sulfate ions specifically? So what's C of SO4 2 minus?
It's still 0.02 moles.
Yeah, you could say that's also equal to 0.02 moles. Good. But for now, that was just a little thought experiment, so you understood that. Good. So anyway, we'll continue on. So we've got C, we've got V. What's our V? Of Na2SO4. 50. Good. And what's our C of our barium nitrate? Pranav?
3.0 times 10 to the power negative 4.
Yeah. And what's our V?
So 0.1 liters. Oh,
100? V of barium nitrate? Yeah, 0.1. Good. All right, so we've got C's and V's. Now, anyone tell me, what should I do now?
Calculate the concentrations in the final mixture.
Very good, right? And this is my tip to you. When you see two different volumes being added, there's no harm in drawing a little beaker and drawing both volumes being added to one another. And that will show you that there is a final volume of solution, right? So what this tells you is what's actually happened is we've diluted the concentrations. Does everyone agree? The 50 ml of sodium sulfate has diluted the concentration of barium nitrate. The 100 ml of barium nitrate has diluted the 0.02 moles per liter of sodium sulfate. So they both now have new diluted concentrations. Does everyone agree? In this new final volume. Now, what is the final volume, Gerald? We've got 50 ml added to 100 ml, so it is
150.
Yeah, right. Now, when you dilute something, what remains the same? Is it the volume, the number of moles, or the concentration that remains the same?
Number of moles.
Number of moles, right? So what I'm going to do now is I'm going to find the number of moles in these solutions. You can either do find number of moles and then go back to finding concentrations, or if you want to be very fast, do C1V1 equals C2V2. Right? Pick what you'd like. How about we go through number of moles today? We can do C1V1, C2V2 later. So what's our number of moles of barium nitrate, everyone? We're going to do that equals to CV. And so that's equal to 3 times 10 to the power negative 4 times 100 times 10 to the power negative 3. What do we get? So we're doing the longer way today, but just times.
3 times 10 to the negative 5.
Good. 3 times 10 to the power negative 5. Let's store that as A. Good. And let's do the same thing for number of moles of sodium sulfate. What do we get? Equals CV equals to 0.02 times 50 times 10 to the power negative 3. What do we get?
One times 10 to minus 3.
Okay, we'll store that as B, right? So now what we can do is we can find the new concentrations of barium. I'm going to put a ruler here, and we're going to start here. So we can find the new concentrations. We can say C of C final. or we can say C2 to be more accurate. So C2 of our barium nitrate is equal to N on V, which is equal to A divided by the new volume, which is the addition of both those two volumes. So it's 150 times 10 to the power negative 3, concentration of sodium sulfate. Sodium sulfate, same principle, N on V is equal to B divided by 150 times 10 to the power negative 3. What do we get? Start with barium nitrate. What do we get as our new concentration? Those of you who did C1V1 equals C2V2 would have got the same answer. So what was your C2, if anyone did the dilution method as well?
Okay, 2 times 10 to the power negative 4.
Good, 2 times 10 to the power negative 4. We'll store that as C. And what was your concentration for sodium sulfate?
Okay, I did a fraction, so 6.67 times 10 to the power negative 3.
Okay, did everyone get the same answers?
Yeah.
Okay, very good. Okay, it's good to see everyone's calculator working is accurate, which is very important. So now, what can we say about barium and sulfate? Because remember, we're trying to find K. And what did I tell you all? To find K, what must you find first? What was the little arrows I drew?
The concentration.
Yeah, so we need to find the concentration of barium and sulfate. I don't care about nitrate. I don't care about the sodium here. So can someone tell me, what is the concentration of barium ions? Is it going to be the exact same as barium nitrate?
Yes.
Yeah, right. You can, if those of you who find it hard to understand that, just think of this like a Lego block, right? It tells you there are 2 pieces of nitrate. That's why there's an NO3 and there's 1 block of barium. So concentration of barium, you want to write this in your exam answer too, to show the marker you understand this, is equal to the concentration of barium nitrate. And that's equal to C. What are the concentration of sulfate? The same as sodium sulfate, right? And that's equal to D. So now can we not just sub in C and D for our concentrations of barium and sulfate, everyone? So we can go, well, KSP, well, we're trying to find if a precipitate will be produced. So would we call it KSP or would we call it QIP?
QIP?
QIP, we don't know whether it's a precipitate yet, right? We don't know if it's saturated, we don't know if it's unsaturated. Remember, whenever you don't know, you'd use a reaction quotient, and in solution equilibria, we call it Q. So you'd say QIP equals to barium multiplied by sulfate, right? And so that's going to be equal to C times D. Very good. What do we get? What's QIP equal to?
1.33 times 10 to the power negative 6.
Good. Now, this question's a bit silly. They shouldn't have given us a temperature. They should have said 25 degrees. So let's assume that it has been given to us. So we've got our 1.33 times 10 to the power negative 6. What are we going to compare Q to determine if a precipitate was produced?
The data sheet.
Yeah, so go to your data sheet and can everyone tell me what is KSP of barium sulfate?
1.08 times 10 to the power negative 10.
Okay, 1.08 times 10 to the power negative 10. So this Q value is times 10 to the power negative 6, aka it's bigger than KSP. Does everyone agree? So what you need to write is therefore QIP is greater than KSP. What does that mean to us? So Athava, what does that tell you? Is a solution unsaturated, saturated, or supersaturated?
It's super saturated.
Very good. It is supersaturated. Think of it like a number line. If Q is greater than K, we've gone past saturation point. It's supersaturated. Therefore, we say there's going to be a clear precipitate. And that is your answer. This is probably the hardest variety of your KSP questions, which is telling you a lot, everyone. It's not that hard. So I guess if I were to break this down into steps for you, what you would need to do is, the question type is, will precipitate form from a reaction. That was the difference here. Did you all realize? What made this question slightly different is they didn't just give you a salt and say, will it precipitate form? They gave you a reaction. Does that make sense? So what you need to do now is you need to find C2 of the ions, and then you simply need to sub it in to find K. So go from C2 to find K. And the way you find C2 is C1 V1 equals C2 V2, or you can use the method we did. It's the exact same thing. And our method is a bit longer, but it was just to show you the logic. In future, you can apply C1 V1 equals C2 V2 to find diluted concentrations, etc. But that's it. And then compare, you'd actually be finding Q. And then you have to compare Q to K. Good. Do we have any questions about this calculation? Did it make sense? I want you to follow as we did. I'm sorry, I accidentally wrote the first part on the right-hand side. You should have done it from left to right. But hope you can still see and follow the chronicity of our working. The equation, data, find C2 using dilution or the method we did, which is find the number of moles and then divide by the new volume. And then finally, compare Q to K. Any questions at all? Good. Good job. All right. So next lesson will probably be our last lesson of module 5. Yeah, it'll be our last lesson. And you will likely be sitting your exam, not the week after that. So not the week after next lesson. Let me just check the specific dates. So right now it's the 30th. You have your lesson on the 6th. And we'll make it the 20th. How about that? So the 13th, we'll spend maybe starting mod 6 or maybe doing more of the trial questions that you flag for me to go through. And on the 20th, you will be sitting your mod 5 exam. Okay, good. You're doing very well. Any questions at all?
Yeah. Do we have to get complete the homework questions by the 20th then?
Yeah, I would encourage you to get as much done by the 20th. I know it's, you know, since I've given you the date quite soon, I can give you all a bit of an extension, but I would expect you all, like for example, if I was a student, I would have finished this probably by the 20th. So aim to get that done by the 20th. Okay. Does anyone have any? Does anyone have any graded assessments right now?
I have in physics one. Not physics. What's it called? 1 week 7.
Okay, those of you who don't have a graded assessment, just smash out these questions. It'll help you a ton. Salva, I may be able to give you a leeway, but you need to message me personally for that. Okay.
Okay, and I have a question.
Yeah.
What page or question should we be up to now?
For homework, you should have.
Yeah.
So coming into this lesson, you should have finished everything up to this page here. So page 102.
Okay.
Okay. So you don't need, remember, I said you don't need to do all the textbook questions. That's up to you, whatever you want to do, but you need to do all of the exam questions you've been given. Okay.
Yeah, Prithvi, for me as well, I've got 2 HSC exams, like on the 22nd and on the 15th.
Which exams do you have?
So I've got Maths Advanced, and then I'm doing Latin as well. So.
Oh, okay. Right. Okay. Well, in that case, what we'll do is, Mitesh, I will give you an extension because the HSC is a pretty crammed time. So yeah, take it easy. Focus on your HSC assessments. And,
I also got an assessment on the 15th, the same maths one.
oh, okay. Well, okay.
Same.
So I guess same with Riasat.
Yeah.
And Gerald, do you also have?
No, I don't have an assessment.
Okay, so I guess the 3 of you, I will give you an extension, given you're sitting your HSC exams. Okay, good. All right. On that note, I'll see you all next week then.
Also, Prithvi, do we just do the questions in like another book? Like, do we just write down the questions and do them?
Yeah, what's going to happen soon is, especially for the next modules, you're going to get all the modules ideally in bulk sent to you, so you can do it actually on the module. I'd prefer you to do that. So that will be organized November 9th-ish. Okay. I think for now, do it in your books. and after that you can do it in the actual booklets when they get sent to you.
Yeah, okay, that's all good.
Good. All right, take care, everyone. Have a good week, and I'll see you next week.
Yep. See you. Thanks.
All right.
Thanks,
See you.
Prithvi.
Thank you, Prithvi.
Thank you.
Thanks,
See you
Prithvi.
all.